Now, I would like to explain to you another important phenomenon in phase lock loop, that is the process of capture. How does the capture actually take place? We understood this for understanding something about this capture range, but actually speaking, how does the capture transient occur? Right. So, again let us examine V naught, because that is one point which will tell us clearly when steady state gets reached. Assuming that originally phase lock loop is having omega I equal to omega naught q, okay, omega I was equal to omega naught q. Now, suddenly omega I changes to some other value, right. So, what happens? Obviously, V naught was at V naught q, omega I was equal to omega naught q. Okay. Suddenly frequency changes, okay, from omega I equal to omega naught q to some other value, okay, either higher or lower. If it is higher, the ultimate steady state V naught should be higher than V naught q, we will assume. If it is lower, ultimate steady state voltage, okay, attained, okay, at V naught should be lower than V naught q. So, let us say it is lower. Omega I applied is less than omega naught q. Now, this is the time axis, let us say. Ultimately, the steady state value should go become equal to this, when omega I is different from omega naught q, okay, but less than omega naught q. Then at the instant of this particular thing, it was equal to omega naught q, and let us say we have produced some kind of sine wave output, because all the harmonics are going to be eliminated by the low pass filter. The fundamental component will have, okay, at every instant of time frequency is changing. Therefore, it is not a sinusoid, but it is something that has narrow, okay, form here and a broadened form here. So, that in effect as a time average it is producing a DC in this direction. Is this clear? Okay. If it is to produce a DC in the other direction, it would have been narrow here and getting broadened on this side. That is, at every instant of time the frequency is changing. So, what I am plotting here is supposed to be the filtered output, but not sinusoidal. Okay. So, it is becoming narrow here, okay, and broadened at this point. So, that on an average it is getting a DC on this direction, and in the next instant of time it will be broader than this here, okay, and this will be still broader than this. Effectively, it is producing a DC in this direction. I mean, this might take place within few cycles, may take few hundreds of such cycles. Okay. That obviously depends upon the low pass filter capacitor, okay, the averaging capacitor, but this is the kind of waveform, okay, with what? Lot of high frequency superimposed over it, because that is not going to be totally eliminated, but will be attenuated considerably. So, you will see a waveform of this type, okay, and this, okay, is called the capture time. Right. After applying the incoming frequency equal to omega I, which is less than omega naught q, it takes certain time for it to capture the incoming frequency, and that is called the capture time. Okay. So, this is how, okay, the output voltage will look like. So, this is in effect the output when you apply a step frequency input, right. Let us say suddenly frequency changes, okay, and again let us say it is brought back to omega naught q, again this will come back. So, you will see that this is the kind of waveform that the FM detector should give as an output if it is given an FSK signal, right. because it is the capture time should be made as small as possible for us to reproduce the square wave faithfully, right. So, this is a design criteria for this. So, we have discussed so far two of the important applications of the phase lock loop. One is straight away for signal conditioning. Signal conditioning means improving the signal to noise ratio, okay, and improving the power level at which the signal gets delivered. Okay. Then again signal conditioning can also be like this, not necessarily selecting the let us say the signal FM signal you want and strengthening it. Also sometimes the what is called synchronization frequency is okay, not continuously coming, where in television receiver horizontal and vertical synchronization pulses are sent not continuously, okay, to be reproduced at the receiving end, but continuously, right. So, what do? You will have two PLLs functioning, one at horizontal synchronization frequency, another at vertical synchronization frequency, getting the composite video at the input. Okay. So, what happens whenever you have the wanted information of horizontal frequency, the output is going to correct itself to the correct DC. So, that output frequency is same as what is coming during those periods, okay, and that voltage is going to be retained because it is going to be a large capacitor, okay, until the next set of information comes. And so, you can extract the synchronization frequency from the composite video using simply a phase lock loop running at the corresponding free running frequency corresponding to the horizontal synchronization pulse or vertical synchronization pulse frequency. Okay. So, that is also forming part of signal conditioning or FM detection, right. FM detection, it can detect obviously FM demodulation, it is an FM demodulation or FSK demodulation, it does not matter, right. FSK is nothing but what? Frequency shift keying used for data transmission. Okay. FM is a regular what? Audio signal modulating a carrier, right. Okay. So, for both these purposes it can be very well used. Prior to this, all the FM demodulators were having limited dynamic range of operation, whereas this particular thing has excellent dynamic range. Okay. I do not know whether you people have studied FM detectors, other FM detectors, you would notice that the FM detection is done by using what? Tuned circuits and locating the carrier off center from the tuned frequency, okay, so that it can produce amplitude variation corresponding to the frequency variation. So, this property was used earlier, whereas in this case you see that we are using a linear VCO, and therefore, the dynamic range of the FM detector depends upon the dynamic range and the characteristics of the VCO. Okay. So, this is an important aspect of PLL as FM detector, and most of the present day FM detectors, okay, are PLL based. Okay. Next important application called frequency synthesis. Now, this is very important in communication, frequency synthesis, particularly for military applications, right, wherein they would like to keep on changing the what? Carrier frequency in a particular sequence known to only them, so that the enemy do not detect the your signal, right. So, this kind of thing is attempted. Now, if you keep on changing the carrier so often, okay, then there should be a perfectly safe way of generating the same stability carriers at the receiving end, that is otherwise no use, right. So, this frequency synthesis is an important synthesis technique adopted in communication. What does it involve? It involves generation of any frequency output with as good a stability as the main source. The main source may come from a crystal. You know that crystal oscillators are the ones which are primarily used for generating stable frequency output. So, crystal oscillator is the main source, right. Generate the reference frequency, and it is so good nowadays that this design has been so perfected that you can get excellent stability with respect to temperature, etc., as far as the frequency of oscillation is concerned, and almost everybody has decided that any accuracy you want in your electronic circuit will depend on a reference, and that reference shall always be, if possible, a frequency reference, not a voltage reference. Okay. It is better than a or time reference. Okay. Even a time reference can be derived from a frequency reference, and therefore, most of the present day control circuitry use as reference frequency, not the good old days this thing technique of using voltage references. Okay. So, crystal oscillator of F reference is coming. How to synthesize output frequency of any value using a given reference is the purpose behind frequency synthesis. Okay. The problem is how to get F naught of any value giving F reference as the input, that is frequency. Now, one or two operations that are needed for this straight away. One is division, frequency division. This division is the simplest operation performed. Okay. How? Division by 2, for example, binary division is done by a multi vibrator, right. You know. So, very simply you can do division by a factor of 2 by using digital circuitry, no problem. So, division by any number can be done again by using counters, right, any integral number, right, integer. So, division by any number n can be done using digital circuitry. That does not solve our problem of frequency synthesis in its entirety. We have to also come up with other methods. Multiplication. That is pretty complex. There is, what is the easiest way of multiplying a frequency? Any nonlinearity. So, that was the age old technique. Microwave engineers, when they were confronted with this problem of frequency synthesis, used diode nonlinearity. Okay. Diode is a nonlinear device. Okay. And therefore, they fed this signal to the diode, and output of that had lot of frequency harmonic components, and they could filter out the desired frequency component. But this is in a very inefficient way of doing, okay, because harmonics will be reducing in amplitude as you try to select higher and higher harmonic components. Now, multiplication therefore had to be done in a better manner. That is the purpose of the phase lock loop. Let us see. A phase lock loop has a phase detector which is nothing but a multiplier, okay, and amplifier plus low pass filter. This is what? Phase detector. I am going to discuss this in two ways. Frequency synthesis can be done by what is called harmonic capture. Right? What is it? We just now said if this is, let us say, free running at, I mean, let us take it is free running at 1 megahertz, and I feed a frequency which is very close to 1 megahertz, then it will capture that, okay, and will keep tracking that. But if I feed at this input, let us say 1/3 of megahertz, right, 1/3 of a megahertz here, it can still capture. At the in the input you have 1/3 of a megahertz, obviously there will be 1 megahertz as the third harmonic in it. So, it can get locked on to the third harmonic component of this signal, right. So, what will be produced at this point is going to be still close to 1 megahertz. Let us say it need not be really 1/3 megahertz, it can be close to 1/3 megahertz. So, if it is close to 1/3 megahertz, this will be close to 1 megahertz locked on to that. That means, now you are selecting the what? Harmonic, right, third harmonic as the output. So, what is the multiplication factor? By a factor of 3. It can now vary around 1/3 megahertz, and this will vary around that. Okay? So, this is called harmonic locking, but this is again not very efficient, because it is the same thing I told you. The phenomenon of capture depends upon the strength of the signal. The strength of the harmonic content keeps on decreasing. Okay? Now, the same argument in the other way also is valid. This can be 1 megahertz, but this can be 1/3 megahertz. Okay? That means, it is called subharmonic locking. So, I can divide and multiply using this harmonic locking principle, right, by any number. But this method is possible, but not in vogue. What is in vogue is this: we will design a VCO, okay, with a frequency counter, programmable counter you put here. That means, this VCO frequency is, let us say, f naught, okay, and this will be f naught by n, or we will call it m. So, this incoming frequency is still Fi. So, what is this thing as far as the phase lock loop is concerned, it does not know what you are doing, right. It thinks that this whole thing is the VCO, right. It still thinks that this whole thing is the VCO. So, it will say Fi should be equal to f naught by m, or f naught is therefore equal to m times Fi. So, you take the output here and you will get frequency multiplication, right. And this is one of the important applications of a phase lock loop, multiplying the frequency by any integer. Okay. So, you said you are going to multiply by any number. So, then let me put another counter here, frequency counter, and feed Fi here. Then this will be Fi by n. So, this is division by n. So, what happens here? Fi by n is equal to f naught by m. That is what happens. These two frequencies should become one and the same. So, f naught therefore becomes equal to m Fi by n. Okay. So, by using this combination of two programmable counters, I can manage to get any m by n. M and n are integral values. Why am I doing this? Now, I can synthesize an output which need not be integral multiple of the input. It can be any number. You can just say 1.212 megahertz I want to generate using 1 megahertz. Let us say you want to generate 1.212 megahertz from an input which is 1 megahertz. Theoretically speaking, this can be done simply by accurately by multiplying by 1212 by divide by 1000. So, this is not an easy job. Okay. Divide by 1000, divide by 1212. These two counters are needed. Okay. And this kind of building counter is not very efficient, but theoretically it can be done. Okay. So, then what else do you need for frequency synthesis? If you say theoretically it can be done, practically what is the problem? Practically bringing this kind of counter itself is not normal affair. Right? So, how do we generate this kind of thing? I can generate this kind of thing, for example, very easily by getting 1.2. How do I get 1.2? Multiply by 12, divide by 10. Okay. Divide by 10 counters are available, divide by 12 counters can be designed easily. So, 1.2 can be got. Then I can get 0.12 because decade counters are readily available. Then I can get 0.012. Then I have to add 1.2 to 0.012 and I can get 1.212. This is the most efficient practical scheme of synthesis. Have you understood the difference? Okay. I simply use commonly available counters, decade counters as far as possible, and the only deviation I am doing is I am designing a divide by 12 counter in addition, which is also possible. Then I go on using decade counters alone, and obtain all this, and therefore, now I can get any frequency therefore to any accuracy by using this technique of what? Addition or subtraction, that is called frequency what? Translation. Okay. So, if you couple on to this scheme of multiplication and division frequency translation scheme, then it becomes a very powerful frequency synthesis procedure. Now, how do I do frequency translation? Can you tell me how? Yes, that is correct, but no, that is not fully correct, because that is all. I simply multiply. So, if I use let us say a multiplier f1 f2, here you will get f1 minus f2 and f1 plus f2. What I want is either f1 plus f2 or f1 minus f2. And now we are talking of f1 being of the order of megahertz and f2 being of the order of maybe kilohertz or hertz, right. If let us say I want 9.999 megahertz, right, then imagine you doing multiplication of 1 megahertz with 1 point maybe 0.00001 megahertz. You are doing that. Then you have to select the corresponding frequency, that is 1 megahertz with let us say you are doing with 1 hertz, right. Then you get 1 megahertz plus 1 hertz, 1 megahertz minus 1 hertz and you want this component, right. This is not a practical joke here, right, that you are now thinking of separating out this, okay. It is not possible. So, what you must therefore do is put this in a phase lock loop, that is what is called frequency translation effect. You have to use a multiplier, but multiplier must be part of the loop. Let us see how it is done. Now, let us see, this is f I, this is delta f, let us say, this is let us say 1 hertz and this is 1 megahertz. Now, what happens here? I will just for your information alone, I will keep track of this 1 megahertz and this is the 1 hertz. This is the multiplier, okay, the same multiplier. Now, I am putting it inside the loop. What is the basic principle? This should become a DC, that is the basic principle, right. So, this frequency will be uniquely 1, let us say this is 1 frequency. If this becomes a DC, because there is a low pass filter here, if this becomes a DC, okay, this should become a single frequency f naught, it cannot be 2 frequencies. If this is f naught, this is going to be f I minus f naught and this is f I plus f naught, right. Obviously, f I plus f naught is going to get eliminated, because that is very high frequency, right, because f naught is going to be very close to f I. So, this is going to be, but f I minus f naught is a low frequency, right. Assuming that it is only one frequency which is lower frequency, that is f naught is less than f I, this is possible. Otherwise, what is coming here is f naught minus f I, not f I minus f naught. Okay. So, if this is f I minus f naught, what will be the component here? F I minus f naught minus delta f, f I minus f naught plus delta f, right. Out of this, okay, again, if f naught is less than f I, okay, then this component can be the DC component. Okay. This is going to be higher frequency component. Okay. If f naught is less than f I, this component can be equal to 0, or f naught is going to be what? F I minus delta f. Right. So, this is the output that we are going to have, and you can select the thing. Now, how are you sure that it is f I minus delta f that is going to be the output and not f I plus delta f? That depends upon the free running frequency of the VCO. If it is closer to f I minus delta f, it will be f I minus delta f. If it is closer to f I plus delta f, it will be f I plus delta f. If it is in between, you can't be too sure what is the one that it is going to capture. Okay. But this is going to be the frequency selected. So, we will continue further in the next class about the other variety of applications which are possible with the phase lock loop in the next class.